Hello students, welcome back to a new video lecture on oscillations and waves. So already before the lockdown itself, we have completed this topic in our regular class, but as a revision I am for your uh, easy understanding during internal examination as a uh, content for reference. You can use this video. I am very quickly revise the whole topic. I'm not going to deal in very detail, but whatever important point to be covered, that I will cover. So this will video as cover as a revision lecture. Okay. So let us see what is exactly oscillations and wave. First, let us see what is oscillatory motion. So to understand what exactly oscillatory motion, first let us understand what is periodic motion. A motion in which uh, which repeats itself after regular interval of time is called as periodic motion. A motion which repeats after regular interval of time is called as periodic motion. If a body in periodic motion executes to and fro motion, then the to and fro motion with respect to a fixed reference point, then it is said to be oscillatory motion. So all oscillatory motions are periodic motion, but all periodic motion need not be oscillatory motion. Example, circular motion is a periodic motion, but it is not a to and fro motion. That's a easy understanding the difference between periodic and oscillatory motion. So next let us see simple harmonic motion. Simple harmonic motion. Simple harmonic motion is defined as a motion in which the acceleration of the body is directly proportional to displacement. That's a very important thing. So acceleration is proportional to displacement of the body from a fixed point and always directed towards the fixed point. That's also very important. Okay, so SHM has important characteristic, that is simple harmonic motion is always periodic in nature. Yes, that should be true always. Periodic. That's the first thing. Second is when body is displaced from mean position, a restoring force acting tends to bring it to the mean position, direct towards the mean position. And simple restoring force is opposite to displacement. Opposite to displacement. The third point is the restoring force is directly proportional to the displacement of the body from its main position. Always the amount of restoring force is directly proportional to displacement. As displacement increases, the restoring force also increases. As displacement decreases, restoring force also decreases. To understand this, you can take a spring and try to stretch. Give a small amount of stretch, you are experiencing small amount of opposing force. As you increase the stretching amount more and more, you find that the opposing force also increases. That means restoring force is directly proportional to displacement. Okay, so it's opposite as well as it is proportional to displacement. So restoring force proportional to displacement. Okay, let us just recall some of the concepts related to simple harmonic motion. The first is displacement. What is displacement? The distance of the particle measured along the path of the motion from its mean position. So displacement is distance of the particle along the path of motion, from its mean position, The second one is amplitude. So the maximum displacement, so amplitude is nothing but maximum displacement of the particle on either side of the mean position. Oscillation. Next concept is oscillation. Oscillation is one complete to and fro motion. The particle about its mean position. Okay. The fourth concept, time period, represented by T. Time period is the time taken by the particle for one complete oscillation. Time taken by the particle to complete one oscillation. Next, frequency, represented by mu, f, etc. Frequency is the number of oscillation completed in 1 second. Generally, that is defined as 1 by T. Sixth, that is phase and phase difference. The phase is a physical quantity in which it signifies the state of the motion and the particle executing simple motion. State of the motion of the particle. In other words, it describes the position and direction of motion of the particle. The phase of the particle expressed as a fraction of periodic time, T, or it's also defined in terms of angle 2 pi. So that is regarding phase. So phase difference is whenever there are two motions, and so what is the difference between their state of motion is defined by the phase difference. Okay, so this is about the concept, small concept. Next, let us move on to, of course, some example for the simple harmonic motion. A mass attached, lower end of the spring, string attached with a bob, etc. Okay, next let us see differential equation for simple harmonic motion. So let us see what exactly differential equation related to simple harmonic motion. So to understand this, consider a mass m. Let's consider a mass m executing a particle of mass m, which is executing a simple harmonic motion. And during simple harmonic motion, let us say y is the displacement of the particle. From its mean position at any time t. At any time, instant of time t. Okay. Then the restoring force F is acting on the particle as is proportional to displacement, or F is equal to minus ky, where k is known as force constant or constant of proportionality. Okay, it's also known as stiffness constant, spring constant, etc. So the negative sign indicates the direction of force is opposite to displacement. Direction of restoring force is opposite to displacement. So therefore force constant is defined as restoring force per unit displacement. Restoring force per unit displacement. Okay, so unit is Newton per meter. So we know force is given as F is equal to ma, Newton's law you can use, where a is nothing but acceleration. So the acceleration can be written in terms of displacement, that is velocity can be written as dy by dt. Acceleration is nothing but differentiation, a is equal to dv by dt, or that is dv is v is nothing but dy by dt, so therefore it is d square y by dt square. So therefore you can write m into m into F is equal to m into d square y by dt square. So there are two equations for force equation. So you can equate m d square y by dt square is equal to minus ky, rearranging the expression d square y by dt square plus ky is equal to 0, or dividing by m you get d square y by dt square plus k by m y is equal to 0. So k by y m can be written as d square y by dt square plus omega square y is equal to 0, or omega square is equal to k by m. So this is an important differential equation. So omega is known as angular frequency. So what is the solution for this differential equation? So there are different forms of solution were given for this differential equation. So we write one by one. The sine or cosine form, let us write y is equal to a sine omega t, that's the general. Sometimes if phase difference is there, phi is written. So y is equal to p sine omega t plus phi, where a is where a is amplitude. Also of course omega t plus phi represents phase, known as initial phase and phase constant. There is an exponential form for this. It is a y is equal to e to the power I omega t plus phi. So this is a three general solution for the differential equation. Next, let us see one more important concept. Next let us see vibration of simple spring mass system or mass suspended to spring, or it's also known as vertical vibration. So to understand this, let us consider a spiral spring where the elastic limit, the tension is proportional to the extension of the spring, that is, it obeys Hooke's law. So in the figure whatever I drawn, let us say spring AB is having length L, is suspended from a support. If a mass M is attached, so when M is attached, the spring get extend it. The spring get stretched by an amount. Okay, so let us say this amount by which the spring is stretched, and you add mass m, the amount of stretching, let us say c. So okay, so BC is the extension, BC is extension. Okay, BC is equal to L. Okay, length increased, let us say BC is equal to L. So due to increase in the length of the spring, force exerted by the spring, so according to Hooke's law, F is equal to minus Kx, where K is the proportionality constant and depends on the material and size of the spring, and the balance tension is S in the spring. Yes, tension is S in the spring. Okay, now let us so yes, S is equal to mg is equal to KL. Okay, this is what exactly the situation. Now if the load is displaced downward, suppose say what you do is this spring, the mass is pulled downwards, so something like this, further stretching. Okay, so this was the mean position, now it is further displaced. So A, B, C, D. So stretched and released, then again its compression takes place. So amount of displacement, let us say X, so on either side. Okay, so CD is equal to X, making total increase in the length by total increase is X by plus L. The tension in this position, let us say S dash, will be proportional to X plus L. That is, you can simply write, I will take as, okay, that's equal to K into X plus L, S dash. So therefore what happens is, resultant force acting on the mass will be the difference in tension. Resultant force F is equal to S minus S dash, or that is equal to mg minus S dash, or that can be written as mg is equal to KL minus K into X plus L. So that is nothing but minus Kx. It's nothing but minus Kx. So F is equal to minus Kx. So then from, of course, whatever we have seen last, Hooke's law, F is equal to ma, acceleration can be written in terms of displacement. Here displacement you took it as x, so therefore a can be written as d square x by dt square. So we can equate the two equation. Okay, equating, you can write m into d square x by dt square is equal to minus kx, rewriting m d square x by dt square plus kx is equal to 0, or further dividing by m d square x by dt square plus k by m x is equal to 0, where you can rewrite this as d square x by dt square plus omega square x is equal to 0. Omega square is equal to k by m. It's an important equation, of course. Alright. So, the time period of oscillation t is equal to 2 pi by omega. That's equal to 2 pi divided by root of k by m, or that's equal to 2 pi into root of m by k. But you know, mg is equal to kl, or k is equal to mg by l. So therefore you can write period as 2 pi into root of m by mg by l, or simply it is t is equal to 2 pi into root of l by g. So g is a gravitational force, l is an important thing. So what is the initial displacement? Based on that, the time period dependent. Of course, that depends on mass also. So this what exactly the period of oscillation. So this is for single spring. So now let us consider the combination of spring. In real life application, we have seen there are different combination of spring. So these springs are either connected in series or parallel. First let us see series connection, then let us see parallel connection. Okay, next let us see vibration of the spring mass system when two or more system when are used, spring are in series. So spring are in series. Okay, let us consider two springs are connected in series. So having let us say S1 and S2 are connected in series. Okay, now if you connect mass, the spring is get stretched. You can see spring is get stretched. First spring is get stretched by an amount of x1, and then second spring, of course straight line I cannot use because already spring is get displaced, so therefore it is dotted line, this amount of extension in the second spring, and total is x. So this what exactly. So let us say stiffness of the spring as S1 and S2 are the stiffness of the spring, and K1, K2 are the respective spring constant. Okay, the increase in length, okay, increase in length, the spring S1, let us you seen that is x1 is a increase, S2 is x2. If x is the total increase in length of the spring system, so therefore x is equal to x1 plus x2. Let me call it as equation 1. Okay, now weight mg causes elongation in the spring, therefore both the spring experience the same. Mg is equal to k1x1 or x1 is equal to mg by k1. Similarly, in the case this corresponds to S1, this corresponds to S1. Similarly for spring S2, mg is equal to k2 x2 or x2 is equal to mg by k2. So therefore equivalent stiffness that is k series. So equivalent stiffness factor combination. So let us say Ks, then mg is equal to Ksx or x is equal to mg by Ks. So let us substitute in equation 1 the value of x, x1 and x2. We get mg by Ks is equal to mg by K1 plus mg by K2. So mg will get cancelled. So you are left with 1 by Ks is equal to 1 by K1 plus 1 by K2. Or Ks is equal to, if only there are two spring, you can simplify this. Okay, this is for two spring, this expression. If there is more than two spring, three springs are there, four springs are there, then 1 by Ks is equal to 1 by K1 plus by K2 plus 1 by K3 plus so on. Whatever number of spring is there, that is get added up. This is a series combination. Next, let us see parallel combination. Okay, before that, just let me give the period expression. Of course, there is not much change. So T is equal to 2 pi root of m by, instead of K, it's Ks, equivalent force constant. So this is what exactly. Next, let us see spring in parallel. Okay, so now let us consider two springs connected in parallel. Okay, they are connected in parallel. So let us assume that a mass m is suspended to this combination. Then what exactly happens? Spring is stretched, okay, by the same amount. So you have connected with mg. So this x is the stretching. So let stiffness factor, so spring S1 and S2 is K1 and K2 respectively. So springs are connected in parallel, so therefore each spring will share the total load. So have the equal elongation, let's say x. So let us say Kp is the equivalent spring constant or stiffness factor for the combination. Then total restoring force is equal to mg is equal to kpx. So restoring force in spring 1, that is k1 into x. The restoring force in spring 2 is k2 into x. So now total restoring force is equal to restoring force in spring S1 and restoring force in S2. So that means kpx is equal to k1x plus k2x. X it will get cancelled, so therefore kp is equal to k1 plus k2. So this is a resultant spring constant for when two springs are connected in parallel. Okay, suppose more than two springs are connected, then Kp is equal to K1 plus K2 plus K3 plus so on. So if you see this expression, so this is similar to capacitor connected in parallel, and series connection is similar to capacitor connected in series. Okay, so there is very clearly it is similar to a capacitor combination. Okay, so with this I will complete this video lecture, this part. In the next part, let us see the different types of simple harmonic motion and other things I will see in the next video. Thank you for watching.